I believe that the science of chemistry alone almost proves that existence of an intelligent creature. A very grateful morning to all. On behalf of the management of J&J College for Women Tenali, myself Anuja, lecturer in Department of Botany, welcome you all for this 5-day international webinar on current trends and future advances in chemical sciences and life sciences. Let us commence our webinar with a prayer song seeking God's divine blessings.
Welcome, Holy Spirit. Be here with your presence. Fill me with your power. Live inside of me. Welcome, Holy Spirit. Be here with your presence. Fill me with your power. Live inside of me. You're the living water, never drying fountain, comforter and counselor. Take complete control. Welcome, Holy Spirit. Be here with your presence. Fill me with your power. Live inside of me.
Before we commence the session, I would like to give you a few instructions. Dear participants, please mute your audio and switch off your video throughout the webinar to avoid inconvenience. If you have any questions during the presentation, please type them to the chat box in your control panel. We will respond to your queries after the session. Thank you for your kind cooperation. It's my privilege to welcome the eminent speaker of the day, Professor, Doctor of Technology, Murthy SSS Chavali Yadav. I request Dr. K. Nirmaljyoti Madam, HOD, Department of Chemistry, to introduce our resource person.
Good morning to all. I am happy to introduce today's eminent resource person, Professor Doctor of Technology, Murthy Sivasatta Srinivasa Chavali Yadav, Professor of Analytical Chemistry and Nanotechnology. He is presently working as Dean in Research and Professor in Chemistry at Alliance University, Bangalore, Karnataka, India. He is Director of Nano India and Director of NTRC, MCE India, and International Nanotech Research Consultant, Higher Education Abroad. He received his BSc in Chemistry in 1990 from Acharya Nagarjuna University, Guntur, AP, India. MSc Technology in Chemistry in 1994 at JNTU, Hyderabad, India, and his PhD Technology in Analytical Chemistry in 2000 to Vienna, Austria, and served as postdoctoral fellow in the United States of America, Japan, as JSPS and VBL fellow, and Taiwan NSC Fellow, Professor Chavali has over 30 years of research experience and 23 years of teaching experience and established 9 advanced research laboratories. He is a recipient of several research felicitations, awards, fellowships, and commendations both nationally and internationally, and has been invited to several countries to speak on his group's research activities. He was listed among world's top 2% scientists for the years 2019, 2020, and 2021, created by Stanford University and elsewhere. He is also a visiting professor, researcher, scientist, fellow at 13 universities in institutes abroad. He was a recipient of over 78 international travel grants. Dr. Technology Murthy Chavali has published widely over 1300 at various international and national stages, which include 370 articles, communiques in reputed peer-reviewed journals, presented at over 270 seminars, symposia, conferences, workshops, over 195 technical reports, and 120 book chapters. He also made a team contribution toward 12 patents. He also focuses on student entrepreneurship, allowing students to learn more than their study in their chosen field by creating an interdisciplinary environment to work and develop. He is also responsible for 7 student startups, mainly converting waste to product, novel product design, and development and usage of waste materials, etc. His research interests are optical waveguide technology, IR sensors, lithium fluoride, chip-based chemical and biochemical sensors, development and application of spectroscopic techniques for the study of nanomaterials. He also focuses on the synthesis and fabrication of various organic, inorganic, nanostructured materials, composites, and nanosensor array technology. Broadly, nanotechnology applications for gas and liquid sensors and nanobionics in plant, fungal, and microbial, nano innovations, nanoforensics, biodiesels, biofuels, biohydrogen, marine engines, algae biomass, fuel cells, biofuel cells, microbial fuel cells, bioeconomy, sustainability, gasification, algae based solid waste management, algal nanotechnology, sustainability, science and engineering, nanocellulose, and diatoms. He received many national and international awards. In the year in the year 1995, he was World Bank Fellowship for survey project for the state of Karnataka, India, entitled Industrial Pollution Survey in India. In the year 2005, he was International Project Taiwan, Canada, worth NTD 28 million INR 45 crores. In the year 2014, he was top 420 analytical scientists in the world. 2014, the analytical scientist. In 2015, he was editorial board member, International Journal of Nanomedicine. In 2016, he was Beacons of the Photonics Industry. In 2020, he was National Level Best PG Chemistry Teacher Award 2020 by the Association of Chemistry Teachers Act. In 2020, he was Stanford University top 2% most influential scientist list for the year 2019 Indian rank. In 2021, he was featured in world ranking of top 2% scientists in the latest 2020 database in ranking. In 2021, he was appeared in AD Scientific Index World Scientist and University Ranking 2020. In 2022, he was editorial board member, Current Indian Science Journal. In 2022, he was appeared in AD Scientific Index World Scientist and University Rankings 2021. In the year 2022, he was review editor for Frontiers in Materials. In 2022, he was featured in Stanford University's world ranking of top 2% scientists. In 2022, he was appeared in AD Scientific Index World Scientist and University Rankings 2022. In 2022, he was editorial board member for Carbohydrate Polymer Technologies and Applications. In 2022, he was editorial board member for Science Progress. In 2022, he was topical advisory panel member of Polymers. So, above listing among world's top 2% scientists for the last 3 years, 2019, 2020, and 2021, created by Stanford University and elsewhere. Thank you, sir, for your achievements.
Thank you, madam. Sir, please take over the section.
Okay. Thank you for your nice introduction. And I'll be talking today about applications of nanotechnology in chemistry and chemical and life sciences, which is going to be a most thrust area of research in almost all the areas and all the universities across India. And I would like to thank the organizers, especially Dr. Sumalata, for giving me this opportunity to talk to the August gathering audience, that too in my native place. And I wish this current trends and future advances in chemical life sciences is going to be a huge success. And with this, I'm going to commence my lecture on applications of nanotechnology in chemical and life sciences. As the time prevails, as for the time given to me, I'll try to explain in detail about some of the examples that we do in chemical and life sciences using nanotechnology as one of the things. Coming to my lecture, this is my first slide, and this is my university administrative building where I'm working as Dean Research and Senior Professor of Chemistry, and also Nodal Officer for International and domestic research collaborations. Our university is 25 years old, and it consists of basically everything, every branch of science, liberal arts, management, law, and we are trying to acquire medicine, pharmacy, and also in biology sectors as of now. And I should congratulate the team of JMG College for Women for organizing this at the right moment, where this is pandemic area, and after the pandemic, conducting such a program where you try to envision every scientist to work on different areas as per the themes of the webinar. And also it has a lot of importance and impact by these international webinars, because it can reach out the larger audience, and at the same time it can boost your own brand awareness, and it can promote your products whatever you developed over a period of time, and at the same time you can be networked among the network, so that it will be highly purposeful webinar content for the entire audience, and it also generate some revenue which can be useful for the institute and also for other things. Anyway, it's a big event, international seminar organized by JMG College for Women for 5 days, and that too in the large scale with, I can see at least 100 participants over here. And with this, I'll try to commence my lecture coming to this topic, applications of nanotechnology in chemical and life sciences. In this particular lecture, I'm going to talk about slightly to give introduction about nanotechnology, nanomaterials, and nanosensors, because most of the examples, applications that I do talk here are related to chemical, biological, medical, healthcare, agriculture, food, etc. Beyond that, I'm not going to talk, as it doesn't seem to be very relevant for the theme of this particular conference. And to make you understand for the students, I'll give some information about why do we need nanotechnology, what are the materials that we use, and how do we progress ahead, how this is going to be useful in our day-to-day life, especially in chemical and life sciences subjects. Plus, our primary research is on nanomaterial development and device fabrication towards nanosensors in various areas. And at the same time, I'll try to conclude on the future aspects, impacts, and dangers that they cause, and also summarize a little bit. And I'll wind up within close to 60 minutes. And if there is anything, we can go ahead with the queries that you raised during my lecture, and I'll try to answer most of them. And specifically, I'm going to stick to biology, medical, healthcare, chemical, and agriculture and food. What is nanotechnology? And it can be defined, as you know, the structures that we play around and manipulate between 1 to 100 nanometers is nothing but nanoscience and nanotechnology. And we can build most of the machines at the molecular scale so that you can encompass and envisage a lot of future development and everything. And typically, we can call this as manipulation of materials at nanoscales, utilizing the quantum effects of these particular materials so that you will be able to derive some of the important precise applications which are required for your day-to-day life, especially in chemical and life sciences. And of course there are a lot of applications on the physical side as well. So with this, if you see this, we have some scaling for a water molecule to tennis ball. We fall under this particular area. If you see the next slide, probably we have a mesoscale nanotechnology, and coming through MEMS, where we have a lot of things which are specific to this. If you approach this particular scale, probably we can work in tandem with these particular structures so that you will be able to probe, you will be able to do so many things. And this nanotechnology regime is completely far less than the diameter of a human hair. That's why it's very difficult, very tedious, and at the same time, it is also highly useful to, after manipulating these materials at atomic scale, that is between 1 and 100 nanometers. We'll try to see how this is going to be useful. What is nanotechnology? It is a multidisciplinary subject, integration of basic sciences and engineering and mathematics put together, like chemistry, physics, biology, engineering, mathematics, which arrived, or we can also say that it is a physical chemistry, physical sciences, life sciences, material science, and engineering put together, which forms an overlapping of this particular section, which is nothing but nanotechnology. That means we need all these principles of science and engineering put together so that you will be able to develop yourself as a nanoscientist. And then, depending on the type of application that you are going to explore, you will be specialized in that particular multidisciplinary area. And since we say about this is an integrated subject, but why do we need nano? We need it because we have a lot of advantages of these particular areas, mainly because of larger surface areas with which we can modify, functionalize these particular things to different applications. And the smaller you make the particle, the greater surface area. Utilizing this one particular parameter, you have n number of applications. As you see, you can start from zero point 0.1 nanometer of a carbon atom, and you can go up to 100,000 nanometers, which is almost less than this, higher than this RBC. And nanometer scale is where the science comes together, because it is going to be integrated part of chemistry, physics, and biology with some engineering aspects, so that we can call this as enabling technology, which is emerging at the nanoscale. As we say, as we speak, it is highly flexible. Based on this particular picture, we can understand this is the thin strand of hair where you have silicon nanowire encompassing this hair, and it is entwined to the hair by passing through the light through this particular fiber. That means this particular wire is thinner than the human strand, hair strand, and at the same time it does the function. And at the same time, you can also understand that this is highly flexible, so that it can be utilized without much of the losses. As you can see on the human strand, this can be applied in different areas, since it is going to be enabling technology, which is the key for 21st century, and with a lot of benefits to the environment. And almost everywhere it is set in every sector of the industry. Why? Because this is an integrated application of biological principles and laws of physics and chemical properties put together. Basically, it is totally an integrated application of sciences, biology, physics, and chemistry at one stage, which started to evolve exclusively from year 2000, and then we don't know where it exactly goes. So that we anticipate a lot of applications in these particular areas. And if you combine this with engineering and technology, probably we can see new areas coming up, like material science and engineering, DNA biosystems, so on and so forth. We'll try to cover some of these particular examples in this particular lecture. And since we are talking about something in the nanomaterial, which is nothing but a billionth of a meter, it can exist and in different structures. And if you compare this 1 billionth of a meter of nanometer to human hair, it is almost close to 80,000 nanometers. And these nanostructured materials do exist in nanoparticles, nanomembranes, nanowires, nanorods, and what else and what. See here some of the examples. Depending on the type of application, you will be able to utilize these things for your specific application where you have highest level of selectivity and sensitivity, so that these structures can be explored for your application. And this is the beauty of this, and this can fly high. This is highly flexible, and at the same time it can be synthesized very easily by controlling just one parameter. We'll see that in the coming slides. And at the same time, since you know these nanomaterials are with improved physical and chemical properties, and these properties change as per the size, and it can also be controlled and manipulated at the atomic level as a building blocks, so that they exist themselves into a essential functional properties. Once you say functional properties, the properties define its major application and deviate from existing applications, and they can be specific utilized in different applications like ion conducting, separation, catalysis, biomaterials, and biosensing. And if you think about what it can deliver fundamental understanding. You can have novel techniques of synthesis and relationships at the nanoscale. And at the same time, preparing this is going to be very low cost once you optimize this high rate of production of these nanoparticles. And these carbon nanotubes can be tailor made and functionalized. You can evolve into novel biomaterials so that these can be highly effective and long lasting catalysts and composites for energy applications, for instance. And it can also act as a strong targets for drug delivery, and so on and so forth. Utilizing the type of structures, type of property, type of optimization, you can use it for different applications, different types of nanostructured materials. That's the beauty of it. And if you see this, once you prepare these particular nano materials, they have highest surface to volume ratio. Most of the materials, they have quantum confinement. That means semiconductors metals will be able to have a lot of applications. Surface plasmon resonance in metals. Super paramagnets can be obtained for these magnetic materials. I have one slide on this particular example. And there is a drastic change in physical properties of these materials. And also these materials can be generating unique properties. For example, opaque substances can become transparent. One of the best examples is copper. Inert materials can become catalyst. Platinum has a structural change. Stable materials turn into combustible. That means aluminum will be auto combustible when you make from micro to nano particles of this particular material. Solids turn into liquids at room temperature. One of the best example is gold. Insulated becomes conductors like silicon because of the tunneling effect. It can be acting as one of the insulator and at the same time as also conductor. So you can also reduce the melting temperature, increase in solubility, so on and so forth. Everything is related to surface volume ratio and quantum confinement of this particular material. So when you evolve from macro, micro to nano, you have drastic and specific set of properties where you will be utilizing these for various applications in your area. And as I said, it is the beauty of this particular synthesis is ease of fabrication. And you can see different types of structures of nanomaterials. All these things are being made of zinc oxide from a controlled synthesis, where they were able to prepare nano belts, nano springs, nano rods, nano circles, nano spheres, nano sphincters, nano spicules, etc., etc. And all these things can be generated by a simple single procedure, but only one variation where that you can alter the shape of this particular nanomaterial, that is temperature. Once you change the temperature, they can evolve themselves into springs, nano belts, nano rods, nano spicules, nano clusters, crystals, nano wires, so on and so forth. This is the beauty of this particular thing. Though it is tedious, but you will be able to develop different types of structures which are useful for your synthesis and application. And another thing is where you can change the pH. By changing the pH, you can develop something like 4 or 5 types of nanostructured materials using the same procedure, where here you keep the temperature as constant and here you keep pH as constant. So all these things can be developed in such a way so that this is one of the simplest way. Once you understand the fundamentals of this nanotechnology, you will be able to synthesize, and once synthesize is optimized, you can produce in a larger scale. And another beauty is the most of the properties which enhance their fields. If you see that one property is going to be in the nanoscale regime. From anything you take, one dimension is going to be in nanoscale regime. That is the beauty of this. By doing so, it can enhance all these particular properties so that this will be useful in their particular respective scale, which becomes a characteristic parameter in that particular model, utilizing these nanostructures and nanomaterials so that this can be availed specifically from their bulk and micro nanoparts. So this is the beauty of attaining the quantum confinement properties for these particular materials once you scale down to nanoscale regime. And at the same time, if there is no improvement, you can also have always enhancement, which is not very common, but still, once you go into nanotechnology, these are automatic. You can see these applications uh, in exponential ways in chemical industry, energy production, energy consumption, and they become green energy systems, environmental systems, and a lot of applications can be seen in novel semiconductor devices and heavy industries. And also, you can miniaturize these systems so that they can become lighter and stronger, used in larger bulk industries like automotive and aircraft industry. These can be used for creating vehicles that can move faster because of the lighter areas, and at the same time stronger, so it becomes much safer. And nanotechnology can be applied to production, processing, safety, packaging, and so on and so forth. So with this, it can be applied from water purification, energy systems, medical, pharmacy, agriculture, food, and large scale infrastructure and auto fabrication area once the size is being reduced in the form of material and also in the form of devices. So these are some of the enhancements that you can see if there is no improvement by applying nanotechnology to your systems. Typically, since we work on sensors, we try to see these particular parameters imparted to our sensors, what we have developed, like precision, accuracy, stability, reliability, low power consumption, inexpensiveness, compact, robust, and smart. Of course, this is one of the typical examples where we have a conductive based polymer sensor or a nanowire. Once it senses, it gets swelled. Once it swells, there is change in resistance or conductivity, and based on that, we will be calculating or comparing this with the analyte concentration so that you will be able to detect at ultra low levels. You can see this is one typical example where you can see something from 100 ppm to 200 ppm, and also you can study the interferences, which if there is any overlap on this, the signal can be from that. So all these things as a sensor characteristics we can study, we can visualize and impart all these particular parameters for the sensor. At the same time, we also need to see and study whether the sensitivity, selectivity, and stability is being compromised. And at the same time, it has to see that it should have a larger shelf life. So reliability, repeatability, and reproducibility is one which we need to answer like 3S and 3R for every sensor that we develop so that it will be useful with all the typical sensor characteristics for a period of time so that human comfort can be attained. And coming to the topic of this particular lecture, which is nothing but application, it can see various applications from energy, defense, metallurgy, electronics, optical, biomedical, agriculture, cosmetic, biotechnology. I'll try to put across some of the examples of these, not covering everything, but try to restrict myself to life sciences and chemical sciences with a slight touch upon agriculture, food, and medicine, or biomedical area, whatever we can call. I'll put them across so that it will give some information to the students and scientists who are working in these particular areas. Since you know nanosensors are existing, they can be applied in wide areas like health, security, defense, energy transfer, housing, and environment. And also, if you talk about life sciences, we have specifically detection of pathogens, agriculture, food, and lab on chip, which can perform the entire diagnostic steps of a hospital in one single chip. And at the same time, you also have applications in environmental side, and it can also have enable sensors in monitoring and analysis. They have portable detectors for highly sensitive toxic gases, and also medical applications where you need to detect something in the zeptomole scale where it is existing in biological applications for biomolecules. And also it can be utilized as integrated part of sensors for existing technology, provide precise and accurate detection from nanomolar to sub-picomolar levels. That means the volume that is being required to analyze these particular molecules have been reduced drastically so that it will enhance the speed of diagnosis. And instead of doing 1,000 samples per day, you can do 10,000 samples. That's the beauty of this particular nanosensors. And it can also probe what is exactly is happening within the cell and within the endoplasmic reticulum, etc., so on and so. We'll see some of the slides over this. And since this lecture is going to be on chemical and life sciences, when you talk biology, that is a vast area for nanotechnology where we see a lot of biological applications, starting from botany, agriculture, food, and medicine, where medicine is one of the peculiar thing with lot many applications and integrative applications of physics and chemistry put together in drug delivery and other sciences which also come under biology. The areas of these particular applications in nanotechnology are far and wide, and it has been integrated to world of biology with several beneficial ways. If one strand coming from biology and integrating that with engineering, medicine, and technology, we will be able to develop a new set of biosystems so that it can be utilizing the nanotechnology for precise way in detecting and diagnosing the cure. So nano medicine, out of all these things from biology, is evolving as a particular interest for both for nanotechnology and researchers worldwide, so that most of the application can be derived from these sectors. And in particular, for everyone who try to work in nanomedicine and biology application, there are a lot many interesting applications where you can put in your experience in your subjects like physics and chemistry in biological side and medicine side, so that you will be able to get some satisfaction out of these particular applications. For example, if you take the latest pandemic COVID, nanotechnology aids in vaccine development, treatment, diagnosis, and also research is still on to realize the possible contribution of nanotechnology to fight against COVID 19. Of course, our group has been working on this over a period of last 2 years, and we were able to produce some 10 papers, of which few of them have been recognized by WHO in what are the methods to mitigate the impact of COVID on humans using nanotechnology is one paper, and what are the consequences of COVID-19 pandemic on solid waste, because most of the masks are being thrown out after using for one day, and that leads to a lot of solid waste management. And this is one area where we try to write about something on solid waste management, especially pertaining to developing countries, that has been given very wide with the strategies giving from nanotechnology. And also, we have written something about research and development in combating COVID 19 using nanotechnology. All these three papers have given utmost importance by WHO, and it has been listed in their database based on nanotechnology aspects to mitigate or control coronavirus. And of course, we do have so many other papers which were related to COVID and other biological life sciences, but not that prevalent as in the case of COVID 19. If you come to applications of nanotechnology in biology, there are great many number of applications like drug delivery, genetic engineering, where you manipulate the genetic material at the lower level, and also you can diagnose and treat cancer treatment using the chemical molecules which aid with nanotechnology and apply in biology, so that you will be able to perform different strategies based on your analysis. And also it can be highly useful in agriculture, where India is the one country which is well below the productivity level compared to all the developing countries put together. So government of India is also concentrating on agriculture, where you can utilize nanotechnology and improve the productivity in agriculture. And in addition to that, you also have diagnostic, detection, and mapping of these particular areas as some of the important areas of nanotechnology in biology. And as the time permits, I'll talk about genetic engineering, drug delivery, etc., and cancer treatment. But since government thrust area is going to be on agriculture, let us talk about something on pesticides and fertilizers, nano urea. Urea is a solid form, and this nano urea is in liquid form. That means by converting urea into liquid state, probably 50 bags of urea can be converted into liquid, and that can be closely equated to 1 liter of a bottle. That means it's easy to carry, highly concentrated, easy to sprinkle in the area in the concentration, so that a lot of benefits can be reaped by preparing this particular area. Our research team is also working on developing this nano area so that it can reap a lot of benefits to our farmers. And at the same time, this cannot be this can also be sprinkled into the soil, but at the same time it can also have some somatal integration of this particular nanourea molecule, so that it can absorb into the body of the plant, so that it can give additional advantages, so that we have evidences that it has improved by 30 to 40% and even 60% some of the crop yields. And you can apply this thing in detection of pathogens, killing the pathogens, and it will also aid in livestock industry and food processing. These are some of the examples where we can employ our sensors and aid to develop agriculture the output. Nanofoods, you have nanotechnology in processing, packaging, products, nutrition, and agriculture. Agriculture, we have seen it. Processing can be done by maintaining the gaseous concentration, unwanted gaseous concentration, while you transport these particular materials. And this can be avoided by packaging these particular products with nano formulations, where it can contain antimicrobials, UV protection, so on and so forth. All these things can be done just by modifying a little bit on this particular area, so that you have vast number of applications, and you can develop some of the nutraceuticals in the nano area, like nano area, and some of the membranes for drinking water purification, so that everything can be simplified, like filtration to ultra filtration, so that it will be an enabling technology using nanotechnology in case of nano foods and food and nutrition. And also we are trying to work on different meat-based analogs, so that which is plant-based analogs can be alternative for meat-based analogs, so that it can be utilized, stored, and consumed, and it can be sensed and detected and diagnosed by nanosensors, where you can apply all these things into that particular area. And in addition to that, you can also utilize this nanotechnology in cosmetics, food, ceramic particles, and clothing. Clothing is one area, in addition to the nanomedicine, where things are going in a very faster rate. Of course, nanomedicine is one important one, and nano clothing is going to be something which is very highly aesthetic of importance. But still, nobody can beat the area of nanomedicine, where it has a lot of things. It has to be analyzed, detected, sensed, and at the same time it can be utilized in a precise way. Current state of the art can detect up to 10 to the power minus 9, but at the same time you can also have able to detect something in the zeptomole concentration. And if you are able to detect something in the minute amounts, that means detection limit is going to be very, very low, and detect minute amounts of foreign material. That means the diagnostic time is going to be reduced. Treatment can be done immediately, and so on and so more forth. You can minimize the damage to the healthy cells, so that proliferation of this particular cancer cells can be stopped, and it can be treated very faster rate. And in medicine, we have, from chemistry point of view, we use different nanomaterials as antimicrobial agents to treatment of wounds, wound healing mechanisms, and so many other areas are still under development. But what exactly we use is nanoparticles, quantum dots, and nanoshells, and nanotubes, and nanobombs, and uh, nanomagnetic materials, which they aid in localized environments where they target this particular compounds, antibiotic compounds, to that localized environment, so that it can be utilized as one of the applications of nanotechnology in medicine. And in addition to that, we can help in enhance the medical imaging by developing nano contrast agents, and it can also use as therapeutics for treating cancer, and it can be used in vitro and in vivo biomedical research. And some of the diagnostic devices can be developed using nanotechnology, and the improvement in analytical tools in detection of cancer like ailments will also be possible. Physical therapy applications, drug delivery vehicles, so on and so forth. The list goes innumerable. And based on the application and integration of different sciences and engineering put together, this will be helping in different sectors in nanotechnology, so that it will be highly useful. Coming to some of the chemical examples, and also we can call it as a biological examples. We started working on different types of sensors like CO sensor, where CO is going to be very toxic, and we started developing something using cobalt oxyhydroxide material, where our sensor, which has been developed using these particular particles, is not a room temperature sensor. So we need to use a heating material, which is ruthenium oxide, where it can elevate the temperature of this particular sensor, so that this will be able to detect the carbon monoxide in the environment up to 250 degrees centigrade. Then we have performed the dynamics and interference studies, where we have obtained, and most of the sensors that we work upon, we don't use this particular material, ruthenium oxide, and we develop some of the material that can work at the room temperature, so that the cost of this particular sensor can be reduced, and at the same time interference can be reduced, and also tedious processes can be eliminated. And we perform the study of gas dynamics, and at the same time interference studies, so on and so forth. And this has been patented as a CO sensor, because this is being taken up by World Health Organization, so that they can implement this in most of the hospitals by converting this into a wireless sensor. And we also developed over a period of time TiO2, SNO2 nanomaterials in combination in 1:8 ratio, so that we'll be able to generate a sensor which is specifically useful for detecting ozone. If you see this particular physical sensor, this is completely different from this type of sensor. Means we try to improve the surface area of this gold electrode here, so that you will be able to have a lot of contact, so that ultra trace levels can be detected by using this type of sensor. And this is a typical conductivity sensor. This is a real world picture of this, where you have a contacts made of platinum and then connected towards the gold electrode. We were able to have precise values with highest level of sensitivity 250, and T90 also stands at 70, which has been improved to 90 so far. And this has been officially commercialized abroad. And this is the particular real world device, where you have TiO2, SNO2 sensors, which is useful for most of the applications in biology and in chemistry. And then we were asked to develop by WHO a NO sensor for bloodstream, because NO is a toxic molecule, a complex toxic molecule at certain concentrations, and this is also responsible for detecting and heart attacks, and also creating blood pressure. So this is one type of sensor where we were asked to develop for NO gas within the bloodstream. That means we are talking something in a gas in the liquid stream rather than gas in gas matrix. So that is one of the challenging thing. But initially we failed in developing something NO gas sensor in a liquid stream like gas and liquid matrix. But initial studies, we thought of developing this in a gas matrix using indium oxide, where the temperature has been highly very high. And to reduce this one, we tried to develop different ratios of indium oxide to tungsten oxide, and finally we prevailed by securing with this particular flow chart from preparing indium oxide tungsten oxide sensor at 1:4 ratio to detect NO gas and gas matrix, so that we will be able to have the dynamics and interference. So it is absolutely T90 and TR90 is going to be highly effective, and we were able to detect something close to 25 ppb, parts per billion level, not even per pm, but it's ppb at room temperature using this particular material. And then we want to take it to the next level, so that we will get into gas into liquid matter, but results are not that sensitive compared to gas and gas matrix to gas and liquid matrix. So we are still working on that, so that we will be crossing ppm barrier to ppb barrier. And at the same time, another application that we were requested by tissue culture laboratory, where they used a lot of formaldehyde. Another application in life sciences, plant tissue culture and animal tissue culture, where they use a lot of formaldehyde in this, which they may use it for a few minutes, but at the same time, these concentrations are going to increase, accumulate over a period of time from morning to evening, that will affect the researchers' health. So we started to work on a new novel material, graphene, but we were unable to produce graphene, and we ended up one step behind producing graphene, which is nothing but graphene oxide. This, after reducing further, it becomes graphene. At that particular level, we try to use this into a different level so that you will be able to detect something which is related to formaldehyde. And we were able to give some modification to this, and this has been published in one of the advanced science letters, where we were able to detect primitively as a primitive type of sensor with a very good dash dynamics, and minimum concentration required to detect is 100, but we were able to achieve 50. Now that we are working on different functionalized material for detecting formaldehyde at almost 150 ppb, parts per billion levels, and it also doesn't have any interferences. And further, we want to take it to the next level using graphene as one of the material. And talking about the same NO and gas matrix, what we thought of is, instead of liquids, probably we need to probe with some of the nano hybrids so that we will be able to overcome the complexity of liquid interference into the gas. But still, again, we failed in this particular thing, and we were able to detect at a lower level using NO gas and gas matrix. For this, we used single wall carbon nanotube TNT nano hybrids. But the beauty of this is we can prepare these particular laboratory scale microwave methods in almost 1 to 2 minutes. And once we prepare different combinations of different concentrations, we were able to test this over a period of 1 week. And then we have found out that these hybrids incorporating the properties of organics and inorganics put together, and we were able to detect something very less than 100 ppb. What we have done with indium oxide and tungsten oxide is going to be in 125 ppm, and this has gone down to ppb levels, where we have a beautiful dynamics with, you can see, number of parameters that we have measured over a period of time is going to be vast, but still the pattern remains the same. Detection is going to be very, very high, and you have a very high uh, R square, where you will be able to detect something in 25 ppm to now we are close to 20 ppb or 25 ppb, so that these hybrids are going to be highly effective for NO gas detection in a gas and gas matrix. And then again, metrology department have asked us to develop something very small which can be able to detect at the lowest possible level to highest level. That means the linearity should be very, very high. So we thought of giving a temperature heterojunction solid state temperature sensor for ethanol measurement. And for this, we have zinc oxide, copper oxide heterojunction sensor, where we were able to increase the sensitivity levels, and it has been given to the metrological standard departments, where we were able to detect something in the order of 50 ppm. You can see the dynamics coming up with a linearity from 250 to 150 ppm without any specific interferences from other places. And coming to the same, we also have some of the humidity interferences in these particular sensors. So we need to have an integrated sensor where you can measure two analytes at the same time, useful for applications in life and chemical sciences. So we probed that with humidity sensor, and in this we need to use something sustainable material. So we started to use hydroxypropyl methyl cellulose with inorganic TEOS nano hybrids, and again, it is also done in 1 minute by microwave synthesis, and we were able to produce. And with all these inputs, GE company has identified as one of the groups working in medical biomedical sensors, and we were asked to develop something for anesthesia, sevoflurane anesthesia. This is the typical structure of sevoflurane, where they use it as an inhaling anesthetic agent so that operation can be performed. But the problem that they have given to us is they have different types of techniques to analyze these sensors, these sevoflurane, but most of these sensors have advanced techniques like LCMS in tandem, NMR, so on and so forth. The cost is going to be like 1.5 to 2 crores. But we were asked to develop something based on a polymer sensor, which can be done like a use and throw by spending around 1,000 rupees or so. The thing is, if you perform 2 3 operations in the operation room, The anesthesia given to the patient in excess will remain in the OR theater so that it will be affecting the doctors and the nurses over a longer period. Because of this, WHO has studied this particular aspect, and they suggested that some of the groups should develop a sensor for anesthetic agents so that it will be minimal, cost effective, and at the same time, it can be eradicated from the hospital theaters. For this, we have taken up this, and this particular molecule has been obtained from another hospital because it is not easily available because this is an anesthetic agent. And we use the same polymer sensors with comb type gold electrode connected to a platinum electrode, and we were able to have a different flow chart so that to maintain the concentration of sevoflurane and then detect in this chemical sensing phenomena. And with this, we have done some molecular studies, and we thought that it is possible to develop a simple polymer based sensor. And we have very crude data where it says it works. And then this has been modified further, refined further, and the dynamics are good. And this has been compared with the high end zero point 0.001 level infrared spectrophotometer, which may cost around 2 to 3 crores. And this has been compared to the existing commercial sensor. We have a beautiful signature of the spectrum compared to ours and compared to the commercially available gas sensor. So with this, it has taken as a next level, and then we were asked to develop something, a wireless sensor. Means we need to involve electronics people so that they will develop a wireless sensor node by segregating a sensor and transmission node, so that we were able to segregate this into sensing area and then transmitting area, and there is no connection between these two, and everything, the signal will be transmitted from a sensing unit to a receiving unit so that you will be able to detect the concentrations of the fifth floor or 10th floor by sitting in the basement. So with that, we were able to do the same type of in a precise way, unlike in the previous way where it has been published, but still we were able to detect something for the percentage of gases. And finally, we were able to go into the lowest possible levels of ppb, and the cost has come down from 1 crore to almost 1 lakh of this particular instrument to be developed for the cause of WHO for having different sensors, wireless sensors in hospital for these particular gases. Now in most of the hospital they have a sensors, a single sensor for multiple analysis, and they transmit the data wirelessly to the base station so that it can be utilized. And after that, we started to work on different types of nanostructured materials where we work on virus and bacteria so that we will be able to detect the changes in the conductivity or resistance of this nanowire so that we can say that this type of virus with that specific signature of resistivity can be present. These are some of the things. These are some of the things that we have done, but we were unable to have a specific biosecurity lab. So we have to stop this one. But some other groups who are working in tandem with us were able to perform all these results. But specifically, these results are not ours because we don't have a biosafety lab. So we have to stop this particular work in acquiring and developing nanostructures for virus-based sensors. And the beauty of this is based on one single type of virus, you will be having a spectral signature. With that, you can qualify, quantify, and qualitatively you can say this specific virus is being present in this. So this is one type of nanotechnology where you use it as a nanobiosensor so that it can be employed, detected in various environments and even hazardous areas. And these can be utilized for ultra sensitivity by using 2-3 arrays on a single platform as a single nanowire biofed, CNT biofed, or even filtration of different nanomaterials that can be by a nanopore biosensor and a nanoparticle biosensor gates using a gold nanoparticles so that you will be able to detect few things. In addition to that, due to the low cost and reduced power consumption and integration possibility, auto operative and wearable, and sometimes it is going to be wireless, these things can be utilized in different areas like uh, connecting the synapses between two synaptic cells. These nanowires can be building blocks or bridging blocks between the synaptics so that the communication can be restored between the synaptic sensors. So some of these can be called as brain materials or smart brain materials. And these can also be utilized in gathering some of the chemical information of the synaptic cell or even in the donor equilibrium so that you will be able to gain some info from these particular cells which are otherwise not possible in day-to-day life. And some of these they can get into a nano needles or a cantilevers. What is the purpose of this particular nano needle? It becomes a near point of contact where exactly it is happening within the localized environment of a cell, so that you can get first-hand information from endoplasmic reticulum where the proteins are being transformed, translocated, so on and so forth. So this gives real world information about the cell, and it has a lot of huge applications, and it can also be probed into localized environment within the cell so that it can give clear cut information for the understanding of the research scientists, so that you will be able to develop something in this particular area where you have typically using the cantilever nano needle tips so that it can give some information on what is existing, what is happening within this particular cell, and so on and so forth. And also, if you have one needle and if you have two other needles, you can study the electrochemical characteristics of a cell, how the electrical voltage is being varied and why it is being changed, what are the groups acting upon, so on and so forth. You can get very simple information, very large data by having a little bit of volume and low concentration. That means you're able to detect, set the detection limits of low concentration, but at the same time, the size limits also going to vary with minimum some pico levels of picoliters or even microliters. You will be able to diagnose whether this is being present in the particular volume or not. So this much is possible, taking the next level of electrochemistry into the next level by means of electrochemical sensing using cantilevers and nanorods and nano needles. And for example, you can probe this particular cell by using these magnetic nanoparticles so that cellular activity can be spied upon by for understanding, for better understanding on the biological activity and the chemical concentrations that are available within the cell, because cell is ultimately the single unit which performs most of the functions, and it also leads to possible detection if there is any variation in the concentration of these particular compounds within the cell. So carcinogenic tumors can be detected, MRI can be screened properly with utmost understanding, and you can also understand the concentration of specific low level compounds or high level requirements, minerals and nutrients which are required. And the contrast of these cells can also be studied as a non-invasive techniques by improving this, so that you will be able to have a better understanding before you get into the next stage of this particular disease. Another useful parameter is you can have one nanoparticle with several therapeutic agents on it, so that all four functions can be done by this particular nanoparticle, which is entangled with other therapeutic agents. So this is also very much possible for multitasking of this multifunctional nanoparticles. And in case of nanomedicine, you have a carcinogenic area in the lungs, and you need to give a treatment cure for this by giving some medicine to it. So if you have a magnetic aerosols which are made of superparamagnetic nanoparticles, and they can be inhaled, and these can be targeted by means of external magnetic field so that the root can be cleared, and you can arrange all these particular materials towards the lung, and it can be localized for treatment. So it fastens the treatment of cancer of the pulmonary tissue, so that the organism can be literally become healthy very fast. So localized magnetic field is one of the areas where you can target these by means of magnetic field, which is a far better application in the nanomedicine. And they use colloidal Ag modified Fe gamma Fe2O3 materials in these particular treatments. As I previously said, it is going to be a multifunctional nanoparticles where you can have 4 to 5 therapeutic agents on one single molecule, so that it can be tagged, localized, directed towards that particular area as in the treatment. And at the same time, some of these nanotubes they can also treated in cancer materials as a nanobombs, and these can be exploded by absorbing energy from IR, and this can be done in two ways: by photoacoustic methods or photothermal methods. Among these two, photothermal methods is one which have little less efficiency than photoacoustic methods, where the healthy cells are being, upon explosion, have been killed or decayed. In case of photoacoustics, this cannot be done, and this has been proven to be one of the best method in treatment by creating shock to the cancer cells and allowing not to proliferate. And at the same time, this can also be used in curing carcinoma tissues within the body by having a magnetic roots, so that these particular materials will go to this area, and then it can be treated in such a way by exposing and shocking this particular cancer cells by photoacoustic methods. So they call it as nanobombs, and it involves integrated application of physics, chemistry, magnetism, and at the same time it can also be utilized in pharmaceutical areas. Yeah, so it is an integrative application so that it can be treated in a better way, so that it will be very useful in nanomedicine. And in 2020, we were asked to develop a sensor for adrenaline, which is nothing but epinephrine, which most of you people know. Though they do exist, everything, but they have a lot of side effects of this epinephrine, and it can also get into potential health crisis due to overdose. Though it has a lot of spectrophotic techniques like TLC, GC, HPLC, UPLC, HPLC, and so on, all these things are going to be either less sensitive or highly expensive material techniques. So we started to work with some of the hospitals abroad, and we were able to produce some material which is based on dual metal oxide and bismuth oxide and cobalt oxide, but we failed in detecting this. And then we incorporated bismuth phosphates with the metal oxides, cobalt oxides, and we were able to develop some electrolytic catalytic oxidation method using a simple setup where we have electrochemical cell and electrochemical device, so that we will be able to detect very low levels of concentration, something very close to 13 millimolar. So with that, we were able to publish this in Journal of Nanoscience and Technology. But still, as per the government needs, it has to be improved further. And we were asked to improve this one. We tried with different materials using the same electrolytic epinephrine electrolytic oxidation mechanism, but we were failed to come to a conclusion to improvement. Though the mechanism this is suggesting it can be improved, but still, for some reasons, it was not we were not able to get into the next level. And finally we thought of trying this with our general nanostructured materials, where we try to use one of the noble metal using doped into tin oxide SnO2 material, and we were able to detect something in the order of 1 millimolar for the same epinephrine. And it is quite a bit of improvement within 6 months from mm, cobalt oxide to bismuth phosphate to PT induced doped SnO2 material for detecting epinephrine. So we were able to detect something in the orders of 13 micromolar, and this is going to be a huge impact on bioelectrochemistry, so that you will be able to have a very slight modification. Only thing is, it has a shell type of structure with which we were able to detect epinephrine at a very low concentration using the same type of mechanism which is followed by cobalt oxide and bismuth oxide mechanism. But the sensitivity has come down drastically from 25 to 13.75 micromolar detection. And then we entered into another biological molecule, paracetamol, and otherwise we call it as S-phenon, because of this, which is widely used, but detection is going to be very rare. But this has been submitted to Journal of Chinese Chemical Society. Still waiting for results that it should be published or not. And similar to that, we started working on levosimendan and also TMAH, which is responsible for a lot of migraines with the body and corrosiveness to skin and eyes and so on and so forth. These two things we are trying to develop something wireless using nanomaterial and electronics put together, integrating on the same platform so that it will be useful for detecting so many other things. And this is being worked in conjunction with several research groups abroad. And some of the people that they've published already on Indian in nanomedicine area from John Hopkins School of Medicine, he was able to study by creating different neurological models how this is going to affect, and this information and input coming from CNS and ocular and system disorders will also be helpful in understanding our area so that we will be able to develop something on that particular line, so that the mechanism to develop a sensor for this levosimendan and TMAH is going to be very, very simpler. And in order to increase the sensitivity, we try to play around with the chemistry. Being on the analytical chemistry side, we try to break the tips of this particular sensor so that it will be highly useful for us to detect and diagnose at a lower levels. And in addition to that, with our previous experience, we were asked to develop so many methods. We were able to develop only 50% of these particular chemicals and methods to detect a simpler ways using our nanosensors, and still 50% are yet to be done. And it's a long way for us to develop these particular methods for these drugs and anesthetic agents, which we can give it to WHO. Why we are using this healthcare nanotechnology in healthcare sector? Because nanostructure materials have a lot of advantages like aspect ratio, surface to volume ratio, and it also comes in reduced power single chip device system, so it can be incorporated into the body so that you will be able to analyze, get the signal at a low cost, and the entire function or purpose which is close to the proximity of natural phenomenon can be done. So we thought of applying this for developing a breath analyzer using TiO2 array detector so that you will be able to say whether that a person is going to be diabetic or not. Just by analyzing acetone content in the breath, we will be able to say what is the level qualitatively and then precisely quantitatively. And this is one of the fast online offline analysis where we have a TiO2 array nanosensor converted into a typical breath analyzer as a device. And this was in place we have done in conjunction with Canadian science government, so that we were able to develop this particular sensor, which is commercialized in Canada. And similar to that, for fresh produce, we have done some ethylene sensor using a nanowire sensor, which also prevailed. And this has been modified further into different types of for analyzing different types of chemical entities, and utilizing the thing on wearable sensors. We are trying to put this on body so that it can give information to your personal doctor, and it can also use it as body monitoring unit, so on and so forth. As you see so many types of wearable devices that has come, we are trying to integrate that with biological, agriculture and food and medical sensors so that it can be utilized. And as I said, government has given a lot of impetus on agriculture, because we are lacking far behind from any of the developing country who were able to understand increasing in productivity by reducing the stress, which the stress can be biotic and abiotic. Abiotic means it can be from extreme physical factors like temperature, drought, flood, and heavy metals and other area. Biotic can be because of other pathogenic microbes like bacteria, fungi, and virus. So by addressing all these things, real-time crop monitoring ensures increase in agriculture produce, precise way of reducing costly agrochemicals, and at the same time minimizing the loss of limited resources like water and nutrients, and so on and so forth. Ultimately, they will enhance the productivity of our agriculture. See, if you see this particular slide, which has been obtained from world bodies, India is far behind Indonesia, Bangladesh, Sri Lanka, Brazil, Thailand, and Pakistan with an output of 2.9. This we want to put it under a cross on par with US, which is over 7. And this can be achieved only by green chemistry and nanotechnology practices that can be put into agriculture industry, so that we will be able to increase by 60% so that we can reach and be placed ahead of developed countries. For this, People have tried to use the MEMS sensors, but we are trying to change this and convert this MEMS into NEMS so that it can be utilized effectively in precision agriculture, so that agriculture losses can be eradicated and improving the produce. And coming to the future, when we talk about chemical and life sciences, most of the future is with biological sciences because it's a vast area comprising agriculture, food, nutrition, medical, and pharmacy. So it is a widespread area of nanotechnology where you see a lot of applications, and at the same time, you should also be economical and production should be in a large scale so that without violating any of these ethical issues in nanotechnology, this can be utilized, and this can be utilized in such a way in drug delivery system, genetic engineering, and there are a lot many challenges that we can overcome utilizing nanotechnology in biology. And at the same time, it also has a lot of impact and dangers in using nanotechnology. You have to be very, very careful. Possible route of exposure to nanomaterials. They can pass through your skin, and of course, it can reach the blood-brain barrier as well. So these are some of the important things that you need to play around with safety with this nanomaterial. Though it has a lot of advantages, it do have some of the disadvantages. So you have to be very, very careful in applying and using these particular materials. So proper safety uh, guard should be taken, and you should be able to work with these things so that it can be useful for everyday comforts of humankind. So nanoparticles defy generalization, and it can be employed in so many other areas with short-term toxicity, and it also has long-term effects, and risk management guidance is also must be made available. And finally, this forms a new and exciting field of research based on different types of applications in chemical and life sciences. And if you integrate this, the possibility of scaling up of this particular application is going to be very wide, and it can be utilized in a different way so that you will be able to play around for a cleaner, better, and greener environment. And utilizing this in environmental protection, biotechnology, medical diagnostics can also improve the value of life, and at the same time it can also be used for different nanobodies, nanostandards, nanometrology, etc., etc., so on and so forth. And with this, probably I'll try to conclude by giving some acknowledgement to my team collaborators across the globe so that we will end up this. And this particular lecture is wide open for any type of question that you want to ask from faculty and students. I'll be more than happy to answer.
Thank you, sir, for your outstanding presentation on nanomaterials and nanostructures, enhancements and typical sensor characters, applications and nanosensors, nanomedicine against COVID-19, etc. We are grateful for the time and effort you took to share your knowledge and thoughts with us, sir. Now
Thank
it's
you.
time. Thank you very much, sir. Now it's time for interaction section. Dear participants, please type your questions in the chat box now. Or you can interact with sir.
Sir,
Yeah.
is nanotechnology new?
No, it is not. It is not new. It is existing over a period of few centuries, probably few thousands of years. But still, we did not realize the potential of this particular nanotechnology, since we have diversified fields in science and technology and subjects across. We were trying to be able to get the impact of this into our areas, so that we think that it is very new, but it is existing from a very, very long time. Only thing
What
is we
about
need to streamline.
oh, what are nanoparticles and nanotubes and nanofilms?
Yes, these are dimensionality structures where you have zero dimensional nanomaterials, nanoparticles, and depending on the type of application. For example, if you want to use it as a OLED screens, probably you need a two-dimensional films like graphene based and something. If you want to use it as a cancer treatment, you need to go for zero dimension, or maybe sometimes to diagnose two dimensional. It depends on type of application that you are going to use. Based on the dimensionality and synthesis, you will be able to produce these things.
Is there the National Nanotechnology Initiative?
Yes, yes, of course. We have a nano mission and running for a few decades, probably, I guess. And there are so many national initiatives across the globe, and so many research fellowships coming up with novel ideas. And of course, almost every university has a nanotech center and nanotechnology research laboratory, which involves a lot of money investment on this. But still, it's a long way to grow while we integrate across the subjects and develop into a multidisciplinary area for a wider set of applications, uh, starting in every sector.
Oh, that's nice of you, sir. Thank you very much.
Yeah.
I am Sushilra from Krishna University, Machilipatnam.
Oh, okay, okay.
Hope there is no further questions. We will proceed to the last session of the day.
Yeah. Thank you.
Now it's time for paper presentation. I request Case Sajni, research scholar at Krishna University, for your to present your paper presentation on the topic synthesis and characterization of nanoparticles. Madam, please start your presentation.
Okay, ma'am. Madam, can you able to see my screen? Hello, madam. Okay, ma'am.
Sajni, please share your PPT.
Yes, ma'am. Okay. Hello.
Okay, okay.
Can you able to see my screen?
Yes, yes, yes. Now you can go.
Good morning to everyone. I am Sajni, doing my research in Krishna University about the synthesis and characterization of nanoparticles in liquid crystalline compounds. And my topic outline is about the what is meant by liquid crystals and their applications, and synthesis and characterization techniques. At firstly, the liquid crystals. What is meant by the liquid crystals? These are the ordered mesophases which are present in between the solid and liquid state. It was first identified in a molecule called cholesterol benzoate by Australian botanist, and it was characterized by German physicist Otto Lehmann. And there are mainly two types of liquid crystals. They are thermotropic and lyotropic. And my topic is mainly on thermotropic liquid crystals. And these thermotropic liquid crystals are again classified into three types: nematic, cholesteric, and cymatic. And these are the various structures. You have seen that I'm these were mainly nematic liquid crystals. They have long range of orientational orders, and they is mainly used in the LCDs. And nowadays, the liquid crystals are mainly used in thermometers, optical isomers, and sensors, and characterization of various cancer diseases also. And firstly, what is the importance of zinc nanoparticles? I mainly used zinc nanoparticles. We can also use the silver, gold, or any other nanoparticles also. But the importance of using the zinc nanoparticles is because they have versatile semiconducting material and wide band and good luminescence properties also. And influence of ZNO nanoparticles in liquid crystals. Liquid crystals acts as a tunable solvent for the dispersion of nanoparticles, and these nanoparticles do not induce significant distortions, and they can enhance the optical properties also, and wide angle view angle also. And the synthesis of we can synthesize the zinc nanoparticles by different methods, like autoclave method, precipitation, and co-precipitation methods also. But I have been used the autoclave method. In this method, the first I have taken zinc nanoparticles in round bottom flask, and I had added these HNO3, 10 ml of HNO3, and for this solution and 10 ml of water, and is have been added and stirred at a certain temperature of about 60 to 80 temperature for 1 hour, and I have added the urea, which acts as a reducing agent, so that the nanoparticles have been reduced into the small sizes by using the high pressure reactor at 120 to 130 temperature pressure. Also, by applying more pressure, we can synthesize the nanoparticles. And these are the various instrumentations I have been used for synthesizing the nanoparticles. And the experimental techniques, that is characterization techniques, I have been used the UV and SEM for analyzing the size of the nanoparticles, and DSC and PON, differential scanning calorimeter, and polarizing microscope have been used for detecting the transition temperature and the enthalpy change also, so that we can characterize the size and what about the cymatic C solid phases. And these are the graphical representation of that compound. These are the some textures I have been seen by using the optical polarizing microscope. And birefringence studies. By using this birefringence, we can determine the view angle. In this birefringence studies, we can have the two types of rays, that is E ray and O ray, which is used for calculating that n value. And by using this birefringence studies, we can calculate the value by using these graphical methods. And these percentages, by increasing the percentage of these zinc nanoparticles, that is from I have been used 8OBA liquid crystalline compound. For that, first I have added 1 weight percent zinc nanoparticle at various wavelengths at 460, 500, and 570, 635. By increasing the weight of the nanoparticles, uh, the wavelength of the also has been increased. We can also characterize the order parameter of these compounds by using this formula 3 cos square theta minus 1 by 2. And by using this formula, we can draw the graphical representation also. And conclusions of my study is about this ZNO nanoparticles effect by increasing the concentration, that is 1 weight percent and 1.5, 2 weight percent, 2.5 dispersion in LC compounds. The pneumatic clearing temperature found to be reduced with increasing the concentration of ZNO while taking the POM and DSC data, that is polarizing microscope and differential scanning calorimetry data. They have no remarkable changes have been observed in the textures that has been used for the dispersion of ZNO nanoparticles. And also the transition temperatures obtained from differential scanning meter and POM are good in agreement with each other, and the slight difference occurs due to their different experimental conditions. The size of the ZNO nanoparticles can be characterized by using SEM scanning electron microscope, which is about 70 to 80 nanometers. The homogeneous dispersion of ZNO in LCs is well determined by using the EDS data of the SEM. And by using the bireferential studies, delta N has been measured by using ORE and ERA calculations by modified spectrometer. That we can find that the spectrometer increase in 1 minus n transitions and suddenly reaching to the maximum value. After this, the percentage of increment of bireferential values is stabilized by the pneumatic regions of ZNO at various weight percentages that has been increased from 9.3 to 32.45 wavelengths in comparison with pure LC compounds respectively. And these are some of the references I have been taken for doing this work. And I have been published this paper in Journal of Applied Spectroscopy. Thank you. Hello. Madam, any questions, please?
Thank you, madam. Thank you for your wonderful presentation.
Any queries, please?
Madam, can you please switch on your video?
Ma'am?
Please share your slides.
Slides. It is visible, ma'am. Madam, is it visible?
No, Sajni.
No.
Okay, it's visible, madam.
Murli sir, is it okay?
Please interact with madam.
Any queries, please?
Madam, there is a question in the chat box. Can you use these nanomaterials in lithium ion battery as a conductor?
No, ma'am. We can't use this lithium in nano battery techniques. Where it is? The chat box. Up to now, this lithium has been not used in this nanoparticles, ma'am. I think so. That is in batteries conduction.
Any question?
Second question. Can you tell me the question, ma'am? Yeah.
Hope there is no further question. We will proceed to the next.
Okay, ma'am.
Ma'am, you are unable to listen.
I request
Yes.
Professor Research Scholar at Krishna University to share your presentation on the topic nanosystems.
Okay, ma'am. Thank you. Is it visible, ma'am?
Yes, sir.
Okay. So, good morning, all of you. Myself, this is Naresh Babu Gachikaila from Research Scholar, Department of Chemistry, Krishna University, Machilipatnam. So, okay, here I want to discuss my research briefly, very briefly. So, I am doing my research on corundum structures of various nanocrystallites, especially iron doped or chromium doped nanocrystallites. What are the topics I am going to cover today? Here I want to discuss. These are the contents what I am going to cover. So introduction about antiferromagnets and introduction about nanomaterials, introduction about corundum structure, Fe 0.7, chromium 1.3 and O3 nanocrystallite, preparation of corundum structure of Fe 0.7, Cr chromium 1.3, O3 nanocrystallite, and X-ray diffraction studies of same nanocrystallite, scanning electron microscopic studies, meaning of that characterization. So by using X-ray diffraction studies and scanning electron microscopy studies means as SEM. By using SEM and X-ray diffraction, how can I characterize that Fe 0.7 Cr 1.3 O3 nanocrystallite and magnetic behavior of same nanocrystallite? Temperature relations, how that temperature varies for that particular nanocrystallites, and Arrhenius plot of Fe 0.7 Cr 1.3 O3 nanocrystallite. Today I'm going to discuss here. So this is my first topic, introduction about antiferromagnets. So basically, recently, antiferromagnets have attracted extensive research interest for future spintonis applications because antiferromagnetic compounds have vigorous applications in industry. So that I'm doing my research on antiferromagnetic properties. Basically, these Fe2O3 and Cr2O3 having a corundum structure, same corundum structure, and they both are antiferromagnetic materials. Here, this point shows that the antiferromagnetic Fe2O3 and Cr2O3 exhibit corundum structure, means Fe2O3 and Cr2O3 both have corundum structure and they both have antiferromagnetic property. So here I am doped that Fe2O3 with the chromium Cr2O3 because they both have antiferromagnetic property as well as they both exhibit corundum structure. That's why I doped iron with Fe2O3 with chromium Cr2O3. Then how that properties are varied. how the formed nanocrystallite magnetic properties varies, the formed nanocrystallite temperature varies. All those things here I was studied. So these materials in the insulating form are attractive for caloritrons, magnonics, and optical extinction of spin waves. So these are the applications of antiferromagnetic materials. The oxides of these materials display magnetoelectric effect also. So the CrO3 in the form of bulk single crystal and exceptional films have become one of the important magnetoelectric effect. So, however, having high Neal temperature of Fe2O3 is substituted in Cr2O3. So here Fe2O3 is substituted in Cr2O3, which gives to enhance the Tn of Cr2O3. So when I was doped Fe2O3 with Cr2O3, then the Neal temperature, whatever it known as the Tn of Cr2O3 is increased. However, the magnetic structure of Cr2O3 and Cr2O3 are different. Fe2O3 are different. Here, Cr2O3 magnetic structure and Fe2O3 magnetic structures are both are different, but the Neal temperature of Cr2O3 is increased when Fe2O3 is doped with Cr2O3. So that is a thing. Uh, so antiferromagnetic coupled chromium oxygen chromium ions along their interlayer Cr2O3, whereas the FeO, Fe ions have ferromagnetic coupling with the layer. So these slides shows some important things, and this is a generally this is a general information about nanomaterials. So what is nanomaterials? How we are used? All these things are covered in this slide, and this is about introduction, coordinate structure of iron doped chromium materials. And this is the preparation of Fe 0.7 CR 1.303 nanocrystallite. So how I can prepare these, I'm explained here. Fe 0.7 CR 1.303 nanocrystallites was synthesized with the co-precipitation technique. So a stoichiometric mixture of CrNO3 thrice and chromium nitrates with 6H2O and FeNO3 6H2O of 0.02 moles were added into 100 ml distilled water as precursors. So here I am taken CrNO3 thrice 6H2O and FeNO3 thrice 6H2O taken as starting materials, and they are taken in 100 ml distilled water. So these three are the starting precursors, starting materials. A water solution of sodium hydroxide, which is 1 molar concentrated, in the quantity of 15 ml, was slowly added into the precursor solution. So whatever the mixture of these three materials, so for this mixture, I was added 50 ml of sodium hydroxide, which has 1 molar concentration. Then there is a precipitate is formed. The precipitate was formed, which is washed thoroughly with distilled water. Whatever the precipitate is formed, that can be washed by using distilled water, and then filtered and dried at 80 degrees centigrade for overnight. So after drying, the hydroxide precipitates flakes were ground into powder. So after drying, hydroxy precipitate flakes were grounded in water. This powder was heated for 6 hours at 900 degrees temperature in air. The ramping rate was set at 2 degrees centigrade per minute, and the cooling rate was 5 degrees centigrade per minute. So then phase analysis of the sample was carried out using pananalytical X-ray diffraction technique. So whatever the nanocrystallite I was prepared, that can be characterized by using X-ray diffraction and scanning electron microscopy. After that, I am studying some magnetical properties and some temperature properties. So this slide shows the X-ray diffraction studies of that particular nanocrystallite, and this is the graph which represents X-ray diffraction pattern. And these are the studies about scanning electron microscopy of that particular nanocrystallite. And this is the image. This is a SEM photo of that particular nanocrystallite. And this slide shows magnetical behavior of iron chromium doped nanocrystallite. And this is a zero field cold and field cold magnetization curve. And these slides shows about the temperature behavior, how the temperature varies, all those things can be discussed by using these graphs also. So this is the Arrhenius plot of the particular nanocrystallites. So this is my presentation today. Thank you.
Thank you, sir, for a clear presentation.
Thank you, ma'am.
Dear participants, please type questions in the chat box or you can interact with us. Sir, please switch on your video. Sir, please switch on your video.
I think sir has been left, ma'am.
Hope there is no further questions. We will proceed to the last session of the day. Now I request M. Kirtana, uh, now I request M. Shekina Kumari Madam, lecturer in chemistry, to propose the vote of thanks.
Thank you, Anuja. This is M. Shekina Kumari, Department of Chemistry. It's my privilege to propose the vote of thanks for this third day of 5-day international webinar. Respected correspondent, principal, vice principal, colleagues, our most valued resource person of the day, and dear participants, on behalf of the entire fraternity of JMJ College, Tenali, it has been such an honor to be a part of this wonderful event on behalf of the organization. I would like to express my heartfelt gratitude to all esteemed delegates of the webinar for their presence and contribution to make this webinar a great success. At first, I extend my gratitude to our honorable speaker of the day, Dr. Murthy sir, to take out time from his busy schedule to grace the event and sharing his valuable thoughts and knowledge with us. Thank you, sir, for your interesting and highly informative and wonderful session of the day. We thank to research scholars for their paper presentations. I express my deep gratitude to our correspondent, Dr. Sister Teresamma Gade, for supporting us to organize their webinar. I express my sincere thanks and special regards to our beloved principal, Dr. Sister Shaini KP, for giving us all the guidance and help to conduct the webinar for the good of community at large. I would like to thank our beloved Vice Principal, Sister Mary Sharada, and Dr. V. Sumalata, convener of International Webinar, K. Bhavani Devi, organizing secretary of webinar, for their supporting and assistance. My sincere thanks to all the members who participate in the webinar and made it a grand success. Thank you one and all. Thank you.
Thank you, one and all. Tomorrow we will meet at the same time.
Thank you, ma'am.